Hello, lovely people. My name is Rohit, and I welcome you all to the CERTIFY podcast series. In this podcast series, we dive into the intricate landscape of IoT with our experts. We explore the risks, vulnerabilities, and solutions shaping the future of connected device. Today, we have incredible honor of speaking with a true pioneer in the field of computer science and applied mathematics. Our guest is Professor Prof Gelenbe, inventor of Chi Network, a distinguished researcher whose contributions have shaped the horizon of theoretical computer science, network modeling, and artificial intelligence. With a portfolio of number of publications, awards, honors, fellowship, his work spans crucial areas including probabilistic automation, stochastic systems, queuing networks, and neural networks. After analyzing the gravity of the guest, I have invited my colleague Rob to help me on this podcast. He himself is a pioneer in the field of IoT. So thanks a lot, both of you, at the podcast.
Yeah, thank you, Rohit. I would like to kick off with a question, Errol, that sort of, as you've also been working a lot prior to the internet, on these notions of networking and things, I would like to sort of asking you, what would you have done different from the TCP/IP protocol that was there with Vint Cerf and Bob Kahn, or maybe you wouldn't have done anything different? But
no, I think we actually did. I mean, we actually did things differently in those days. In fact, it's well documented. We all use Zoom, like the three of us are now on Zoom, right? And or something similar.
Yes.
And we all actually in those days, I developed something which was a precursor of Zoom. And it's patented, so it's documented. It was based on, I mean, the concept then, because the internet didn't exist. Now,
Yes.
the internet exists, but it's, as we see right now, it's highly unreliable. It's quite easy to disrupt a communication. I've seen it happen many times. For instance, a few days ago, I had a Zoom communication over the internet with about 30 people, and the whole thing was a mess. Okay, and 30 is not such a big number, actually, if you think about it. And what we did at that time, in the 1980s, we developed and patented a system for communications which was based on establishing communications with a switch, which was basically a packet switch. So everyone would kind of have a packet connection to one point. And then the switch would very rapidly switch everyone to everyone so that people could talk at the same time or see each other at the same time. Okay.
Yeah.
And it even had a name. It was called the Sycomore, Sycomore switch. And it was patented for Thales, what is now called Thales. At that time, it was called Thomson CSF. Now, if you look at an article, a recent article, relatively recent from last year in IEEE Spectrum, it is open access. I can send it to you. It explains all this. Right. Okay. So we were viewing things differently. We viewed, because we thought that networks would be unreliable, and they are. We thought that we should, for instance, if you're setting up a communication, you should go to some kind of specialized server, which does a many-to-many switch for you in real time and at minimum cost in terms of graph theory. And that's basically what the invention was. So we were thinking of things differently. We would think that communications you would have to set up, if you wanted to be very efficient, you'd have to go to a place, from your point, you'd have to connect to a place. And everyone who could connect, who wanted to talk to you at that time, would connect to that place and exchange very rapidly. Of course, we didn't think of this for transferring files, but we thought about this for transferring voice, and for having a real-time voice communication, for having a real-time video communication. So there were, alternatives. The only reason why the internet protocol and the way it is today is working, I mean, why everyone is using it, is that its business model is very low cost. That's really the only reason. okay? Because for a ridiculously low fee, we are all communicating. In fact, most of us communicate free of charge over the internet. But then in exchange for that, there are lots of things that we don't have. We don't have security, we don't have quality of service, and so on.
Yeah.
Okay.
Yes, I think so.
So the answer is
TCP
yes. I mean, we did. I mean, and what we did was one example. Others took, we kept the packet idea, because the packet idea is actually had preceded, was a long time, 20 years before the internet, there was already the packet idea, which was there. It had been developed by some people initially at the UK Post Office, and then at the British Telecom. So the packet idea was there. I mean, not just the idea, but the implementation was there. And we used that to propose a technology for point-to-point communication of a large number of people, so that they would be all switched and share their flows in real time for voice or for video. And there were other proposals which did not use the packet idea, which were called ATM, for instance. And ATM was actually running, IBM was running that until the end of the 90s. So there have been many alternatives. And the only reason we're using the current system is that it's so cheap.
Yeah. And it's so, it's all about speed.
That's why we get spam.
Yeah.
I mean,
Yeah. And when you say sort of there were alternatives, was there also any relation at that time with policy? I mean, at the moment, there's lots of...
Well, when I say there were, I mean, you say there were alternatives. In fact, there are. And many of these technologies are still being used, but they're being used in special purpose environments.
I see.
Okay, not where special purpose means that they're kind of fairly expensive installations, but these still exist. They're used, for instance, for military communications and for very highly secure video conferencing. So, you know, when people talk to, you know, for battlefield communications and so on, we don't use the internet as we know it, you know, as you and I are using it now. It's used like the internet is still being used as an auxiliary, but many other things are being used.
Yeah. Yeah, and they have this history that you mentioned, that you talked about. Sort of they
Exactly. All of these things, you know, they're being used, but they're not being used by the general public that wants to talk free of charge.
Yeah. Yeah. I think that's the power of this internet and this TCP/IP is pass on a packet.
You know, for instance, if you take a bunch of pilots flying aircraft and perhaps talking to each other with video and so on, they don't use the internet.
Yeah.
Obviously. For all kinds of reasons.
Yeah. And this is also a field that is kind of a thread in your work, a thread throughout your work.
Well, then, and then later on, after we did that work, I developed optimized, using reinforcement learning, optimized routing. So how do you, instead of just saying, okay, the internet is routing like this and it's for everyone, suppose you have access to a certain number of routers in the internet. How do you optimize your routing so that at each instant you get the best for each participant? And this is again something that we don't have today in the common internet. I mean, you have common routing rules, but there is no optimization for the purpose. And we developed those algorithms. They were published. This is documented stuff. It's called the cognitive packet network algorithm. Again, it's used, if you look at the number of citations that it has had from other patents. Okay, this particular patent has had a large number of citations for other patents. That means that it's been used as part of many other systems.
Yeah.
right? So yes, so this kind of work of how you actually optimize networks has been part of my research over the years.
Yeah, because I always wondered. So the work of Vincerf, Bob Kahn on the TCP/IP protocol, actually sort of designing the protocol, you also design the notion of data. That's sort of the very notion of data is designed by designing the protocol. And so I think it's not such a strange idea or a strange result that we have all these big companies in Silicon Valley very close to where the protocol was designed. As it moved so quickly across the world, and as you say, there's no security involved. Would there still be kind of a way in Europe that we could make this more accessible to people for a low cost or for some fee, or to think about a new network structure? Is that
Well, I mean, the whole business model has been, as you're aware, has been pushing, in a certain sense, communications out of the market. So the communications companies, mobile phone companies, which are offering us a very fundamental service, have been pushed into very low margins. And they cannot invest. They're not able, at such low margins, they cannot invest because they cannot attract the capital that allows them to invest. Okay? And on the other hand, the high margins are the people who are making the big money, are the Googles, they're the Microsofts and so on that are exploiting this bandwidth.
Yeah.
But with a lot of software which remains proprietary.
Yeah.
So it's just the whole business model that has turned itself, if you wish, upside down.
Yeah.
And now perhaps we will see once people realize that we are dealing with monopolies actually, in the Googles and Microsofts and so on become monopolies, okay? So as people see that and as governments see that, they will start, I think, switching and then the market will open up again.
Yeah.
And in the US, we start hearing about that because it actually defies the fair business model that the US proclaims.
Yeah.
If you have a monopoly for all information, if you have a monopoly for all information services, which is basically what Google is doing, and you have a monopoly for all software services, which is what Microsoft is doing, a quasi-monopoly, I mean, you're against the free business model.
Yeah.
You're not giving the competition a chance. And in the past, there's an example where the US, for instance, considered that AT&T was a monopoly. And Bell Labs and AT&T and so on were monopolies. And that's what led to their, in a certain sense, destruction. Yeah. And this may happen again. We'll see. But certainly, but these are long cycles. The internet did not happen quickly.
No.
You must realize that the internet took a very long time to happen. The basic work that you're talking about with Bob Kahn and so on, where they ran the first experiments and came up with TCP/IP, that happened in around 75.
Yeah, something like
1975. That. And it took about 25 years for that to establish itself as the major means of computer communications.
Yeah.
So these cycles are very long.
Yeah. Yeah, but I'm happy to say I'm happy to hear that you say that these are cycles, and because sometimes we think that something that the current situation is kind of set in stone and it's never going to change. And
no, the only thing I've seen which is set in stone is that there's always change.
Yeah.
right? For instance, and the change is kind of interesting. I don't know if you've noticed that Microsoft has decided to buy one of the reactors at 3 Mile Island in Pennsylvania.
Yes.
So that's an example of vertical integration where the computer industry says, well, I actually need electricity, and to get electricity, I need nuclear.
Yeah.
So these things are, it takes, and I'm sure the US government will not want to see a monopoly which includes nuclear and computer industry.
No, but still, yes.
So it's going to be very interesting to see how these things go. But
Yeah.
by and large, I think, first of all, the idea that there is just one kind of communications going on is false.
Yeah.
Okay. Currently, there is not one kind of communication that's going on. I mean, everything gets connected somewhere to the internet, but there are many different kinds of communications going on.
Yeah.
That's one thing.
Yeah.
Certainly, for instance, the way 5G, 6G are done at the cell level and so on, that is not the internet. That's a totally different technology.
Yeah.
And many others in special purpose communications, special purpose video communications in enterprises, in the financial world, and so on. A lot of these things are not general purpose internet. We just must realize that.
Yes, that's really important.
Market-wise, they may not be, or number of user-wise. I shouldn't say market-wise, because, as I said, the internet at the network level is not really a very profitable business. So there isn't much money there to be made. But if you look at the whole, usage of the internet, that's a big market. Now, that is a big market. But then there are many other markets where people make a lot of money.
Yeah.
And after all, a few billion here, a few billion there is a lot of money.
Yeah. Yes. To sort of to quickly go a little bit back to your point about the telcos and about the telecommunications not being able to invest. That's also kind of a bit a serious situation, isn't it? Or it's also this part of this change that their function will go or will move to another layer, but still it's also about keeping the networks in shape and investing.
Of course, I mean, if you look at the only telco that has been able to invest heavily in the last 10 years is Huawei.
Yeah.
Okay. Now, to what extent is it good for all of us that there is just one country in the world that can invest in telcos? Is it good for us? I don't think so.
Yeah, no.
Yeah, and then of course, then we say, okay, then they will not have this part of the market, they will not have that part of the market. But the end result is that the only one in the world that in the last 10 years has made substantial amount of money and has invested substantially is Huawei.
Yeah.
So that should be, strategically a question mark for us.
Yeah. 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 Absolutely. Absolutely. Have you been following a little bit the way that the new commission has divided kind of the technological sovereignty part and sort of all of these different
the most recent EU Commission, you're saying?
Yeah.
No, I haven't. I think it's a bit related to Thierry Breton's departure.
It's possible, yes. Yeah.
Now, Thierry Breton was in a very powerful position, not just because of the politics, but also because of his background.
Yeah.
Okay. Thierry Breton is not a standard politician. He's a businessman.
Yeah.
So he was in a very strong position to understand how to do things.
Yeah.
And he was also taking some positions which were unpopular with the Googles and so on.
Yeah, very much so. Yeah.
Yeah. So we'll see how it goes. I don't think that
Yeah.
every change, well, we'll see how it goes. I don't know how they're cutting it up now. But yeah.
Yeah.
I think it's useful to have technologists who are, actually commissioners in Brussels.
Yes.
Just having politicians and people with a legal background is not necessarily very good.
No, I fully agree with you. I think so. The Commission has about 17 acts and directives, and they're all very necessary. But I think compliance alone, and then also these fines, are not sufficient for a 500 million zone to actually think about strategic autonomy. And when you think about the fact that in 2010, the 12 top politicians in the Chinese government, out of these 12 top politicians, 9 were engineers and scientists.
Sure.
Wen Jiabo was an engineer and a scientist, and he designated a lot of cities as IoT cities that have now really grown to a large extent. And he was calling the Internet of Things wisdom of the earth. And this was in 2010. So fully agree with you that we need technologists and people who understand what's going on at the top in the heart of these decision-making systems.
Who don't need to turn to 50 advisors to know what the simple answer is.
No, exactly.
Take them 3 minutes to figure it out, and then they should move on from there. And that's the problem with having just people with a political experience and kind of a legal experience in such positions, because they don't have the quick answer. They don't know. So they turn to advisors and so on. Well, it's good that they turn on to advisors, but then they waste a lot of money, and then they take the average of what all of the advisors say, which is not necessarily very helpful.
No, it's indeed. I fully agree. I think so. I think so too. In a way, I think the European Commission has sort of understood what is happening, which is.
I'm looking, for instance,
yeah.
there's a very interesting example now. France had a visionary president called Charles de Gaulle. Now, why was this guy visionary? Because he had I don't know whether you know about this, but he was essentially a tank commander.
Yes.
So he was in the most technological part of the army, his career. In the First World War, he was one of the pioneer tank commanders. So he realized that, radio and motors and supply lines and supply chains and getting the oil into the tank and repairing the treads on the tank and all that stuff, he understood that this was capital to be able to conduct warfare.
Yeah.
And he had this understanding that technology was absolutely essential to a society. So he invested in nuclear, he invested in electricity, he invested in computers. He was doing all of these things way before his time.
Yeah.
Because, he had this experience. He didn't need an advisor to tell him that he needed an engine to run a tank.
Yeah. Yeah.
While, for someone who's a legal expert, first of all, they don't even imagine that they need tanks. And then the cars, just press a button and they go, right?
Yeah.
And when they don't work, you take them to the garage and someone will take care of it.
Yeah. No, this thinking then probably also led to the French internet before the internet.
That's right. And in fact, when you say about when the internet prize was given, the £4 million prize was given for the internet, one of the 4 people who got it is a Frenchman, Louis Pouzin.
Ah, I didn't know.
You didn't know that? Well, he was the inventor of datagrams. And in fact, he did the basic invention in the TCP IP protocol. The TCP IP protocol was copied from his notion of datagrams.
Okay. I didn't know. No, that's very, yeah.
Right. So Louis Pouzin, Pouzn, and fortunately, they didn't forget him.
Yeah.
Because there was Khan, of course. Basically, the prize was shared between the people who did the web,
Yeah.
right? The web got a fourth, the datagrams got a fourth, and then the two who did the TCP/IP, who kind of implemented it, got half.
Yeah.
But that was how it was split. So, as you know, the web was CERN. CERN did the web.
Yeah. Tim Berners-Lee, yes, TBL, yeah.
CERN, well, we always associate the name, but it was basically done at CERN. And we don't know, exactly who programmed it first and so on. It's always complicated. And then there was Pouzin. Pouzin was a person, but there was a team behind him. And I knew some of them are still alive.
That's
and
a very
most of them
interesting
are still
story.
alive. Pouzin is
Yeah.
still alive, and most,
Yeah.
except for one person who was a key person, Hubert Zimmermann. He passed away from cancer quite young, and the others are around.
Well, there's a story there then. Yeah.
And then
Yeah.
I built the first fiber optics Ethernet. Back in the early 80s. So we were doing a lot of these things when I was in France. So we were doing a lot of these things because they seemed to be the obvious things to do.
Yeah.
And
that was that was at INRA?
I had my team. I was already a university professor, but I had a team which was partly at the university and partly at INRIA.
Yeah, yeah.
Okay, so I did both the many-to-many communications that I mentioned. I did it with my university hat, but the patents have my name on them. There are 2 patents. They have my name on them. And then I did the optical network at the university.
See.
And the motivation, the way we got it funded, it's always interesting to know who paid for it, right?
Yeah.
Who was paying for it. And we got it funded through a company that was interested in doing communications for nuclear environments. Okay, and the idea was that in nuclear environments, you have a lot of noise, a lot of electromagnetic noise. And therefore, you have extremely rich electromagnetic spectrum. Okay, therefore, your connections, including your coax cables, are going to pick up the noise. So you'd better use fiber.
Yeah.
Because you don't pick up electromagnetic noise. And that was you see? So it's kind of interesting to see why things are done and how they are done in technology.
Yeah. Yeah.
But and the application was the IoT, was measurement inside the nuclear power station.
Yeah. And were the sensors not affected by that noise, by that?
Well, the sensors were stuck on. A sensor is not an antenna. A sensor is something which is stuck onto a device, which is measuring something, right? Directly measuring. So the signal there is stronger than the noise.
See.
But when you put it on a wire, then the wire catches a lot of noise. So you have to avoid wires, and therefore we're using fiber.
Yeah.
And we were using random access, which is a very robust protocol, which is the Ethernet protocol. We were using random access, and I had just before that done a paper on the optimization of random access of Ethernet.
Yeah.
I could tell you much more about
Yeah,
that.
yeah. No, it's fascinating. Sort of, I was thinking. So imagine that
So
yeah,
you look at all my medals and you say,
yeah,
why did the guy get them?
yeah,
Typically,
yeah,
people who say we are kind of nominating him, and he's the guy who did this and this and this, and here's the documentation.
yeah. Yeah, no, that's it's yes, that makes a lot of sense after hearing this. And then I was thinking, sort of, what would you say to young people that are now, let's say, in their 20s, and that they want to study these networks and this network theory. And so what would you say that they would need to do, or what do you think that the challenges are for now, if you look into how the situation is evolving?
Uh, well, first of all, I still think that you really need to understand the technology. Okay, so you need to understand the theory to be able to take the following steps. I mean, we need a lot of people who don't understand the theory and who basically are technicians. We tell them, do this, do this, do that. They do it, and it's fine. Okay, we need those people. But those are not the people who lead the pack. All right?
Yeah,
The people, if you look at the people who lead the pack, who really come up with the innovative ideas, including the ones who establish the major corporations, these are people with very strong educational basis. Okay, Google was established by two people who had graduated, who had a PhD from Stanford. Okay, one of them was the son of a computer science professor whom I know personally, who I knew. He passed away. His father passed away fairly young because he always had something associated with his chest. So he had, chest infections and things like that. The
yeah,
father of Page. One of the two is called Page. One is Brin,
yeah,
the other is Page. Page's father, Carl Page, I knew him
yeah,
personally, and he passed away. He was a computer science professor, and his son was very well educated in math and physics and so on. And he went on to do a computer science PhD at Stanford. So if you look at the very strong Bob Kahn,
yeah,
was an MIT graduate. Okay, so these people are, Louis Pouzin went to École Polytechnique in Paris. So these
yeah,
are people who had very strong technical educations and understood the technology and could criticize it and go to the next step. So I think we still need those people.
yeah,
And we particularly need those people in Europe. Unfortunately, in Europe, contrary to the US, we're not getting enough of those.
yeah. Is it a lack of educational context, would you say, or?
No, it's the fact. It's the fact that the PhD track in Europe is not viewed to be very rewarding. Okay, contrary to the US, where you have, of course, a lot of Americans who go to MIT then want to make money, right?
Yeah,
Which is fine. So they want to do a bachelor's at MIT, then go and work and so on. But you have a substantial number of people who go on and get PhDs among the best, the most capable Americans. Okay. Then, of course, the US also imports people from India who are very good, come from the IITs and so on, and they import people from abroad and from Turkey and from Greece and from et cetera, et cetera, et cetera. Okay. But we in Europe do not have the same ability. We
yeah,
have not put our act together to do that.
yeah. it's also a different mindset than, in a way, I think, sort of it's
You know, Poland, for instance, where
Yeah.
I work, is one of the biggest producers in Europe per capita of engineers. And they cannot find PhD students because they can't convince their own people to do a PhD.
So
basically, they don't pay. It's very simple. You have to pay engineering and science PhDs roughly what they would make if they went to a company.
yeah.
Right? I mean, there's
Yeah.
no magic, because
No.
you have these young people, they want to have a car, they see their friends who can go to a restaurant and so on. Then you pay them an amount of money where they cannot even pay their rent.
Yeah. Yeah. No, it's sort of, and this, I think, also is something that needs to be discussed with policy, because these are the key issues why certain things are not happening in Europe.
That's right.
And as you say, these, if we put them all together like you're doing, it's actually not rocket science to do them, but there's a certain amount of steps that need to be taken.
Well, there's also the problem in Europe where they say, oh, all PhDs should be paid the same. Okay? All PhD students should be paid the same. Oh, I mean, if he's doing archaeology, or if she's doing a PhD on 15th century painting, she should be paid the same as, etc. Then they say, well, if we pay all of these people at the industry rate, we'll have much fewer PhDs.
Yeah.
All of this is true, but you just cannot ignore the fact that unless you pay the people decently,
Yeah.
you'll not get them to do this kind of thing, which is essential.
Yeah. Yeah.
For instance, even in France, things have deteriorated considerably. Back when I was in France running a team, okay, I could recruit people coming from the best schools, engineering graduates, okay, into a position where they could do a PhD and where they were encouraged to do a PhD, but I could pay them a decent salary.
Yeah.
Not exactly the same. You know, for instance, if I'm going to talk in today's terms.
Yeah.
If it was 5,000 euros for a beginning engineer in a company,
Yeah.
right, I could pay them 4,000
Yeah.
to do research.
Yeah.
At that differential, the motivated people would come because it was more fun, more interesting. They could get to travel. They could go to the US for a conference and so on. This attracts the people for the difference.
Yeah, and they could learn. they could learn.
Exactly. But if you say, oh no, today the entry level salary in France for a good engineer is 5,000 euros. The entry level for a PhD is 2,000.
Yeah.
Before taxes.
Yeah.
With 2,000, after they've paid their taxes, they can barely pay their rent.
Yeah.
This is just idiotic.
Yeah. And is this not also are these things not sort of taken up in the IEEEs? Is there not a working group there?
IEEE is something which is specific to each country. So IEEE does not really cut across things. It's basically, IEEE is just a thing for organizing conferences, for exchange of information, and for journals and so on. But it's not something for solving societal problems or addressing societal issues.
No. But it has working groups, doesn't it?
But working groups are about this or that other topic.
Yeah.
It's about working groups about the IoT, about this or the other. I mean, the reason why IEEE exists is not to solve this kind of problem. It is to deal with the exchange of information at the national and international level.
But maybe it's sort of, if we, maybe a working group on these issues that actually affect directly the real situation on the ground would not be a bad idea, or
but IEEE is not the right place.
No.
I mean, the right place is to either the European Commission or a national government that says, how can I change the rules? And changing the rules in a democracy is very difficult. because you have this idea that the archaeologist equals the engineer, which is true, in a sense, because they're all good people and they're doing useful things and so on. But you just cannot fill, PhD positions at the salary of a PhD in archaeology.
No, I think but I will.
Well, you asked about the fundamental question. I raised it.
Yeah.
And I think those questions we have to really address seriously.
Absolutely. Yes. I will. I'm taking notes. I'll take notes, and I will make. I will try to get this into the direction of the people that I know in the Commission doing IoT and in DG Connect. Yes. Just sort of to go
for
back
instance, they give grants, right? They give grants, and then the grant goes to, say, an institute in France that pays PhD. So the money goes to this institute, and the institute applies the local rules.
Yeah.
And the EU is very happy with that, right? But that's the wrong way to go.
Yeah.
Because with that, you're not going to attract the best and the brightest.
No, but I think what you're saying is fundamental. This is fundamental to the situation.
From India, an IIT student from India go to France if they can go to the US for a much better deal.
Yeah.
Right?
No, absolutely. Absolutely. This needs to be addressed. Definitely. Yeah. These are fundamental issues. I fully agree. Maybe just to go back a little bit.
Yep.
Because you mentioned supply chain.
Yep.
And when we mention supply chain today, we immediately think about security.
Of course.
Is there? Do you have a specific view on that at the moment?
My big take on supply chains and security for the IoT is the following comment, and which I see in the DOS project, as I saw in IoTAC, as I saw in all of the IoT projects I was involved in. Okay, I think the people doing this are too much computer scientists, software people. Okay, they think that if they do this at the software level, the world is fine. To me, this is nonsense. Why? Because the IoT is about things. Things. They're physical objects. Okay, so the security of the IoT is the same thing, is integrated with the security of the things themselves. So we absolutely need to take this on board. And I take the DOS project, for instance. Fortunately, there's no one officially representing the DOS project here, because otherwise they would shout at me. The DOS project, I think, is just saying, I have verified that the software here is okay. To me, this is nonsense, okay? Because the real problem is, how about the device and what it does? And we saw this wonderful example, wonderful, of course, very sad example, but wonderful example of this happening with the explosions in Lebanon.
Yeah.
Okay. This was a supply chain attack.
Yeah.
And you tell the people at DOS that this is a supply chain attack, they'll say no. But it is. The supply chain is all the parts, all the components that go into the system. Okay? And once you start tampering with the devices themselves, what was exploding? It was the IoT devices that were exploding.
Yeah.
It wasn't the software that was exploding. Okay? Was the software tampered to give the explosion? Of course. It had to interpret, the software had to be modified so that it would have to interpret a command and then generate an electric current. So there was a tampering of the software, a tampering of the hardware, in addition to placing the explosive material.
Yeah.
Okay? However, our cars, our smart cars, are by definition explosive materials because our batteries can explode.
Yes.
So they don't even have to go and place a new battery there to make it explode. They just have to tamper the circuitry.
Yeah.
That you can do when you're building the devices, the chips. You can
Yeah.
tamper the circuitry when you're building the devices, and you can tamper the software when you're uploading the software.
Yeah.
So our cars are by definition tamperable, insecure IoT devices.
Yeah, that's very serious. That's a very serious situation. Yeah, yeah.
And this is true for our cars, it's
Yeah.
true for our city buses, it's true for a lot of things. Okay?
So
Because
they
cars, electric cars are
Yeah.
exploding spontaneously.
Yeah.
Right?
So
Just means that someone can make them to
Yeah.
explode if they get to it. They can get
Yeah.
organized and make them
Yeah.
explode.
Yeah. So basically, all of these individual items become mission critical in a way. Sort of.
Exactly. And we need to take an approach where we integrate the physical with the electronic, which is also physical actually,
Yeah.
and with the software.
Yeah.
We need to start thinking in that way in a lot of these projects, which actually we used to do a long time ago.
Yeah. And do you see any progression beyond the FPGA boards that which is kind of this beginning of this kind of integration between software and hardware? Do you see that there's going to be a progression there or some work in there or?
Well, I don't think you were around at a meeting in DOS where I told them, I had just come from last October. I just come back from the US, and I went to my American alma mater, which is New York University, and I was talking to people who were working on IoT security, and they were actually looking at the circuitry. So trying to understand whether the circuitry had been tampered with. Okay, because the first thing you look at is the circuitry behaving as it should. Okay, but there you have to do physical measurements. You have to measure the currents and voltages. You just can't look at the software. Because if someone has tampered with your devices, it has tampered with its behavior. And the behavior is illustrated by the electrical currents and voltages in the system.
Yeah.
Okay, so we need to integrate all of that. And these people were funded by DARPA.
Yeah.
So we absolutely need to, especially, in our world where we're depending critically on components that are coming from far away, from China or from Taiwan or wherever, we need to be able to look at these components, but look at them from their physical behavior aspect, not just saying, oh, is the software fine?
Yeah. And so sort of we now have this European Defence Fund. Sort of, I think that they don't want to really mimic this notion, this DARPA, because I think that the beauty of the DARPA situation is also that if you have a good one-pager, you can also get funded.
Right.
Sort of, and here we are. We have, which is sometimes also good to do a lot of paper, but still sometimes these.
I mean, if we wanted to, out of this meeting, if we wanted to do something real, I think we should do a one-pager for the European Fund, Defense Fund.
I would love to. Yes, definitely. Yes. Yeah.
I think that would be very important because, after all, we need to be very alert. We can't just sit on our backsides. I could have used a kind of more explicit word. Yeah. We can't just sit on our backsides and happily say, oh, I've gone to Murcia for the project meeting and it went well. We were all kind of happy. And we all talked about how nice we have our supply chain and blah, blah. That's fine. Okay, good. The problem is that we are overlooking all the stuff. And we better start looking at those questions.
Yeah. No, I think I fully agree.
As you notice, I mean, the thing I dislike most is complacency.
Yeah.
we've had our lunch, we're going to have our dinner, and in between we can have our nap.
Yeah. No, I fully agree. Yesterday I was in Brussels in a workshop and a conference on technical sovereignty for Europe. And it was quite an amazing setup. It was carried by 5 political parties. There were 3 MPs. There were people. There was sort of the head of a signal company. There were people talking about the India stack that is running quite amazingly and is going very fast on this horizontal layer of payment. And also Brazil has done this horizontal layer of payment now, sort of removing lots of charges from all kinds of banks. And I think it's a good moment to discuss this. Yes, absolutely, it's a good moment.
So I think, with the IoT and the supply chains, certainly the security of vehicles, consider the following attack on a vehicle. You put some software that says, if the car gets above 80 kilometers an hour, okay, send a current into some part of the battery, which provokes a heat up and an explosion.
Yeah.
That's a very nice attack.
Yeah.
Or other very nice things, we have sensors in tires these days, right? So you can also, if you have a sensor in a tire, you can also put an actuator.
Yeah.
So when the tire, the heat of the tire indicates that the speed of the car or something is above something, you can increase a current going in one place, creating a hole in the tire. How about that?
Yeah.
Burning a hole in the tire. And lots of opportunities like that.
Yeah. 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 No, it's and I think it's to actually devise the attack and to do the attack is I think is one thing, but to actually defend against that,
Right.
you need a very holistic vision.
Exactly.
Sort of. So
Exactly. But
yeah.
you must be able to imagine attacks that way.
Yeah.
You must be able to imagine what it might be. And that's another little problem we have with today's computer science background. Rohit, I don't want to kind of, I don't know if you have a purely computer science background. I don't. I'm an engineer.
I have completely computer science. So
So
I learn more
often,
information
in my
technology.
classes, when I teach, I say, look, your laptops are slow. Don't you think so? Yes, because I'd like to put this, that, and the other, and make my laptop fast. So I said, why don't we increase the clock speed of your laptop? And they look at me and say, that's a good idea. They don't realize that, if you increase, because of the physical behavior of the circuits, if you increase the clock speed, the waveforms change. The waveforms become much more like they were continuous, and at some point they don't act. The system stops acting as a digital device, and that's where the computer just can't work. That's why it's actually working at the maximum speed, because they are designed to work at their maximum speed. And if you change the clock and try to make them go faster, it will just break down all the signaling inside the computer. Okay, but a lot of people don't understand this, and unless for instance, in my background, we had, as engineers, we had machine shop, we'd go into the machine shop and we built metal objects, right? We had chemical experiments, we had all kinds of things that would give us the physical context of what we were doing. And when I went back to the US, I got my PhD in the US, but when I went back there in the 90s to be a department head, and I was there for 10 years as a department head, I realized how much American computer industry depended on the electronics, the mechanics, disk drives depend highly on aerodynamics. No one in Europe knows how to make disk drives.
Yeah.
Why? Because it takes very sophisticated mechanics.
Yeah.
Okay. No one in Europe knows how to make chips of all kinds. Why? Because it takes a lot of sophisticated chemistry, a lot of sophisticated physical etching.
But we do have ASML. I mean,
that's true. The Dutch have their very good company that sells devices. Yeah. It's a physics company.
Yeah.
You're absolutely right. But I think we lack in Europe. We have lost our ability to work, across multiple levels of industry.
Yeah.
We still have Zeiss Icon. We still have Leica in small versions, etc. So we still have some things, but I think we really lack this ability to work across a large number of technology sectors.
Absolutely, and this is the right moment to address this sort of in this one pager, because it's at the moment in the European Commission, and it's all about industrial policy.
Yeah.
And so this is the right moment to address these issues, including the issues of the PhD and the engineers. That is key to build this educational context.
Well, I've written a report where I was proposing, actually, even with numbers, I'll bring it out, about this issue of engineering PhDs and the numbers that are needed and so on. So yeah, but it falls on deaf ears as soon as it gets into ministries, because they say, the minister in general, for instance, the current minister for universities in France, the one that's just been appointed, his background is, guess what? He's a law professor.
Yeah.
Okay.
Yeah. Yeah. But
a totally different vision of what research is all about.
Yeah.
Research of a law professor is looking at the previous, decisions in various courts. That's the research they do.
No, absolutely. I think what we've seen in the past decades is this wave of connectivity has hit the United States, and it's done what it's doing best there, which is building these rich individuals, sort of, and not profiting the state, but just having these rich individuals that are now building these companies that are worth 7 trillion. In China, the engineers immediately got it. They run a big bubble on deep packet inspection, and they control everything within it, which is they control infrastructure, hardware, software, applications, services, which is actually the way that we should also do, but without the vision on distrust that's running in the system.
Right.
But we need the same kind of vision of this, and in Europe, like you said, we got the lawyers and the engineers, and what are they doing? They're regulating. So they're now coming out with 17 acts and directives, from the CHIP Act to the Cyber Resilience Act to the AI Act. And I think that we see or understand that compliance alone is not going to build this a 500 million zone in which we need all this connectivity in the right way.
We're getting to the end of our hour here.
Yes.
So I think we did raise some interesting issues.
Yes.
And some next steps.
Yes.
I think for the IoT, the big message that I'd like to provide is that we have to look at the physical system because after all, the IoT is there for a purpose. It's not there just to send network packets. The purpose of the IoT is to measure and control.
Yeah.
Okay, and measure and control physical objects. That's why it's called the IoT rather than the internet.
Yeah.
And therefore, we have to really integrate. When we look at the security issues, we must integrate the physical aspects, including the physical aspects of the supply chain. Okay? Because the supply chain includes transportation. It includes assembly. Assembly is essentially a physical process. It's taking parts and putting them together into boxes. Okay, so we're doing assembly. We're doing even the supply chain itself is physical. because of the transportation issues, because of the manufacturing issues, because of the mounting issues on common substrates and so on. All that stuff is physical work. It's physical.
Yeah.
So we really need to include the physical in the notion of supply chain and in its security aspects.
Yeah, I think this is the important message, and I want to thank you very much for this wonderful story and information and sense of urgency. So thank you very much.
Thank you. Thank you all.
Yes.
Thanks.
So
thanks for giving us this opportunity for this chat, and perhaps this can lead into some interesting future projects.
Absolutely. Absolutely.
Definitely, yeah.
Okay. Thank you very much.
Thank you,
Goodbye.
Rob, for
Bye.
setting